The only thing that can really change what it's doing sideways is a little bit of the air resistance. But we're just gonna get rid of that small effect because it's only like really 2 or 3%. So we'll just get rid of that a little bit. That number doesn't change. That one has to change because there's a planet that speeds things up and down if they're directed up and down. And some of this 50 meters per second is up and down. Gravity affects this, but not that. Okay. So here's an arrow at an angle. I break it into what it's doing sideways and what it's doing up and down. Sideways, there is no acceleration. And all the distance equals rate times time. But up and down, there's a planet that is accelerating that object. Okay, so when I take a look at this, if I can read that, because I know what does it say. Okay, so right here, I'm going to say t equals 0 seconds, right there, in this box. So here's right where it gets launched. So at 0 seconds right at the start of the problem, acceleration sideways, 0. Acceleration in the y direction, gravity. Gravity. I'm going to call that 10 meters per second per second. Because what I'll do, I'll call everything going up positive and then coming down negative. Velocity, x direction, sideways. Right when it starts, it's 40 meters per second. When it comes off the person's foot, it's flying sideways at 40, and I'm just going to call going to the right positive. Velocity in the y direction right when I start is 30 meters per second. Okay, if I just do that and nothing else, I could already answer a whole bunch of questions about what this object's going to do. I already know exactly how long it's going to take to hit the peak, which means I really know how long it's in the air for. Just looking at those two components, 40 and 30. This one right here, the 30 gets affected by gravity. Gravity changes that number by 10 meters per second every single second it's in the air for. So how long does it take gravity to pull that thing to 0 when it knocks 10 out of it every single second? It takes 3 seconds, right? After 1 second, it's down to 20. So I change it by 10. The next second, I go from 20 to 10 because I knocked out 10. And then the next second, I go from 10 to 0. It takes 3 seconds to hit the peak. It's the peak in 3 seconds. It's the ground in 3 more seconds. It's in the air for 6 seconds. I already kind of know that. I think I could answer probably some other questions about this object too, without really probably breaking too much of a sweat. But here's what's happening. Here the ball is sort of flying up, so let's call that 1 second. Acceleration sideways, still 0. We're not going to allow the air to affect it. There's still a planet. There's still acceleration in the y direction. How fast is it going sideways? It cannot change because there is nothing physically there that can make it speed up or slow down. It's still going 40 meters per second sideways. But how fast is it going in the y direction? Well, now it's going 20 straight up because it started going up at 30, but gravity changes that by 10 every single second that the object is in the air for. That's 20 meters per second. If that makes sense to you, that's the whole shebang. There's nothing else. Gravity affects velocities up and down. It does not affect when it's flying sideways. Sideways, it started off at 40. It's still going 40 sideways, but the velocity in the y direction changes by 10. That's what gravity does. It grabs this number, changes it by 10 meters per second every single second that it's in the air for. So when I hit this next spot, I'm going to call this 2 seconds. It still has no acceleration sideways. There's still a planet pulling down on it. Sideways, it's still going 40 meters per second. And up and down, how fast is it going? Yeah, it better be just about 10 meters per second. So you see how your thinking is going, what's going on sideways? Really nothing. We're not allowing any changes sideways, because we'll just get rid of that little bit of 2% effect. But we can't get rid of the planet on this thing. So there's still this acceleration that only affects this component. So right when it hits the peak, it looks like to me that's at 3 seconds. So there is still no acceleration sideways. Acceleration in the y direction. Is there still a planet there?
Go.
Yeah, there's still a planet there. Sideways, going 40 meters per second. Up and down, what's the velocity? 0. Isn't that how in chapter 2 we picked up the peak? It was no longer going up or down? That's still true. The velocity in the y direction is 0, but it's still flying sideways. Right? It's still going this way. Every time you see it, it's still going sideways. It's just not going up, it's not going down. And so that's how fast it's, oh, okay, I'll get to another question in a moment. It's kind of interesting. Okay, so it looks like maybe this is at 4 seconds. Acceleration sideways, nope, that's always gonna be a 0. Acceleration in the y direction is downwards. There's still a planet pulling on it. That's still at 10 meters per second. Velocity sideways is still 40. And how fast is it going in the y direction? 10, but
Negative.
this way. So I need to call that 10 meters per second with a minus sign. 10 meters per second with a minus sign. Okay, so I hit this position over here. I guess that's at the 5-second spot. There's no acceleration sideways, up and down. There's still a planet pulling on this object, changing its speed by 10 meters per second every single second it's in the air for. Sideways, it's still going 40 meters per second. And now up and down, its speed is 20 with a minus sign. Now, some of you have made this error already on last week's quiz, and that is when you talk about a final velocity and so forth. People talk about a final velocity. Eventually this thing is going to hit the ground and bounce around a little bit and then stop. That's what objects do. The final velocity here is not 0. When people talk about final velocity, they really mean the velocity that it smacks into the ground with. Then it's going to go to 0 and so forth. So just as it's getting ready to smack in the ground here, that's at 6 seconds. We have no acceleration sideways. We have a planet acting on it still, just as it's getting ready to smack into the ground. It hits the ground going at 40 meters per second sideways, and the velocity sideways now is up to 30 meters per second, but that's now down. So, where is the object? Where is the object going the slowest? At the peak. As long as it's in the air, it always has this component of 40. But then it also has this component up and down. But when it hits the peak, that component up and down is shrunk to 0, and that's how we identify the peak. There is no vector up and down, so when you add the vectors up, there's nothing to add up and down. So if you hit it with a radar gun, the velocity, the speed, right? The radar gun doesn't really tell you how it's moving, it just tells you how fast it's going. So as you watch it, as it flies through the air, it's changing constantly, because gravity is affecting its speed. But when it hits the peak, I know exactly what the radar gun should say. It's going to be measuring 40 meters per second, because that's the only component that's left alive at the peak. Now, if you hit it at 5 seconds, I can't do that in my head. I have to actually go do it for calculation. But it will calculate what the radar gun is saying at 5 seconds. But I've got more work to do for any spot other than the peak, because now I've got 2 components, I have to add them up. So, okay, so any questions that we have up here so far about like something like a projectile? This analysis is pretty simple. The hard part is when you read the word, you have to start asking yourself, what are they really asking me for? I think the hard question here is something like this. At t equals, let me just pick 4 seconds. What is the velocity of the object? At t equals 4 seconds, what is the velocity of the object? And then I come over here and say, okay, well, here's 1 second, 2 seconds. What, 4 seconds? The velocity of the object is 40. No. The object velocity is 10 down. No. Neither one of those are the velocities. The velocity is that vector plus that vector. This is what it's doing sideways. That's what it's doing up and down. And velocity is a number and it's a direction. I know what the components are. That is, the sideways and the up and down. You have to put those together to get the answer. On a picture, how do you add vectors? Head to tail. I put them head to tail, and it's going to tell me exactly what the answer is supposed to be. So I think I'm going to try to do that here in a moment. So yeah, let's just pick a spot here at 4 seconds or something like that. So maybe I'll just use this middle space here. So at, let's say that the question here is this one. At t equals 4 seconds, what is the velocity of the projectile? I'm going to add my vector components together. They have to go on a picture to get the right direction, otherwise the direction won't be right. Head to tail. So at 4 seconds, I've got a velocity of 40 sideways. So it doesn't matter which one you start with at all. The velocity sideways is always 40 meters per second. Head to tail. So I need to go to this one's arrowhead and connect up the other one's tail, and that one's worth 10, and it's worth 10, but going down. Oh, looks like that. So we don't need the minus sign in the triangle. But they go together head to tail. Here's what it's doing sideways. That's its component. Here's what it's doing up and down. And so the actual velocity, that is if you hit it with a radar gun, the radar gun doesn't tell you 40, it doesn't tell you 10, it tells you this number right here. That's the velocity when t equals 4 seconds. So maybe I'll say velocity when t equals 4. You need to know what that number is. That's how fast it's going. So the analysis is done with what happens sideways, with what happens up and down, but now I have a question about, what is the thing just doing? Not sideways, not up and down. What's it actually doing? Well, I have to get my sideways information, my up and down information, and add them together to get the true answer. X's and Y's must meet at right angles by definition. So how do I find the size of that? 40 squared plus 10 squared, add them together, take the square root, the answer is a little bit bigger than 40. But that's what I need to do here. So to find the size of that vector, we're looking at a right triangle. So the notation is this. The size of the vector, put absolute values because that's only half the answer, is 40 meters per second squared. And this one is 10 meters per second, but when you square it, it doesn't really matter if you put that negative in there or not. 40 squared is 1600, 100 squared is 10, we need the square root of 1700. What is that? 41. So t equals 4 is 41. Okay, if you hit it with a radar gun, it will say 41 meters per second, and particularly right at that instant. That is half of our answer. The other half is the direction, because a vector is a number and a direction, and usually, unless you are given north, south, east, and west, the direction is always with respect to the x-axis. Here's the x-axis. I'm going to give an angle with respect to that x-axis. So I'm going to grab that angle right there. I know the opposite side, I know the adjacent side, and I know the hypotenuse. So you can really use a sine or a cosine or a tangent here. It'll make no difference. We'll always get the same angle. But just the way I've got it labeled up there, maybe I would just use the tangent of that angle. Is the opposite, tangent is the opposite side. However, the adjacent side, 40 meters per second. And it tells you what this angle is going to be. So I really need 0.25 and take the inverse tangent, make sure you're in the degree mode. 0.25, inverse tangent, 14 degrees. Okay. Usually I think you're going to see words hooked onto that angle. It's 14 degrees below horizontal because the object is coming down. There were some times when it was heading up where the velocity would be like this. You'd have an x component and a y component. Then you say so many degrees above the horizontal, but here I think it's 14 degrees below horizontal, or below the x-axis. Below horizontal. Okay, so what do you take away from this? Two things. Anytime something acts at an angle, your analysis will always be broken into what is taking place sideways, what's taking place up and down, and do them separately. Do them separately. If you have to put all the information back together, like we did here, then you do so. Okay, so it's a big deal that we realize that this sideways motion has nothing to do with the up and down motion. They are completely independent of each other. But there is a connection between the two. That is, I can take information from what's happening up and down and bring it over here. But the only way to do so is through t. There's a t here, and there's t's over here. So if I were to be asked a question like I have right here, t is 4 seconds, I can find out what it's doing sideways. I can also figure out what it's doing up and down. So I mean, what would be the next question that somebody would ask you? Maybe what's its position at 4 seconds? Can you figure out where it is in 4 seconds? Yeah, and at 4 seconds, it's traveling for 4 seconds, and it's going 40 meters per second every second, sideways. So it has flown sideways 160 meters. Where is it up and down? How would I figure that out?
Bring that first and then
I'll just go to this right here. Mm-hmm. So at 4 seconds, right, it has a position. So if the question happened to be, you know, where is that spot right there? You can't do it in one step, but what you would do is you would calculate this, how far sideways it went. And the way you would calculate that is this way. It's traveling for 4 seconds. It's doing 40 meters per second. It's gone 160 meters. So if you're trying to find the coordinates of that point, that's one of your coordinates, how far sideways. It's the up and down that's always the harder one because that's the one that's got the accelerations. But that's what you already did in chapter 2. So you said, well, it's changed in position in the y direction. I had to know how it started in the y direction. And at least half of you will do this, and I don't know why. If you put that 50 meters per second into that equation, or that, or that, or that, right? You're just gonna get a big yuck on your paper. That 50 meters per second there is what the object is doing at an angle. This is not at an angle, this is sideways. These are not at angles, these are up and downs. That 50 meters per second never goes into pieces, ever. That 50, the first step is to break it into 40 and 30. 40 is that number, 30 is that number, is that number, is that number. That 30 is what was it doing up and down at the start. That 50 never shows up here at all. But if I want to know where it is up and down, I think I'm going to go to this, but that's going to be 30. That's going to be 4 seconds. Acceleration due to gravity, yep, that's going to be 10 down. I'm going to let the thing travel for 4 seconds. And it's going to tell me where it is from where it started, which is actually here, the height. It'll do it in one step, and it'll tell you exactly what that coordinate is. Exactly the same problem that you did before, except that it's flying sideways now. But the sideways motion has nothing to do with the up and down at all. Very cool. Okay, so, any questions on this piece of paper? You know, when you look at a test or a homework quiz or something like that, that you get this, you know, the softball here for part A. Because you have to do it anyway, and so you might as well, you know, get some points for this one. It says a cannonball is launched at 37 degrees with a velocity of 100 meters per second. What are the components of the velocity? Anytime a vector is acting at an angle, this is exactly what you're going to do, whether you are asked to do this or not. Cannonball is launched at 37 degrees with a velocity of 100 meters per second. What are the components of the velocity? There's no physics here. There's nothing here other than your analysis has to use the components. These are component equations. This is a component equation. 100 meters per second never goes into any of these kinematics because it's not a number in the y direction. Yeah, it's not a number in the x direction. So I think, you know, when I read something like this, the first thing I'm going to do is just kind of sketch out, you know, what's taking place. The velocity of the object is 100 meters per second at 37 degrees with the horizontal. So some of that 100 meters per second is sideways. Some of that is initially up and down. So the up and down needs to be initial because that's the one that changes by 10 every single second. But it should really just be a matter of just like a minute or two for you to run to your calculator, use sines and cosines to figure out these two components. And that should be that. So adjacent hypotenuse, that is the cosine. So the cosine of 37 is the adjacent side all over the hypotenuse. That's one equation, one unknown. That'll tell me that x component very fast. Cosine of 37 is, maybe that's, 24. So this is going to be 8. Let's just go my calculator. 37 cosine. Yeah, okay, yeah, so yeah, 60. So this is 80 meters per second. If I want to find that initial y component, opposite side from this 37, and I know the hypotenuse, I'll use the sine. Sine of 37 is the opposite side, all over the hypotenuse. Sine of 37, so you just take 37, take sine, k tells you 0.6 times it by 100, and you get 60 meters per second. can actually do some physics. That is, now you can tell me physically what the thing might be doing at different spots. Just looking at those two components, I think I already know how long it takes to hit the peak. Which means I know how long it's in the air for. How long is that thing in the air for? How much? Yeah, 12 should be jumping into your head, because gravity is going to change that number by 10 every single second. It's going to take 6 seconds to get to the peak, where it's not going up, it's not going down, but it's still going sideways. So 6 seconds to the peak, it's going to be then 6 seconds hit the ground, it's in the air for 12 seconds. Maybe that's part B, I don't know, let's take a look. No, it's not. How high will the cannonball go? How high will it go? You need to translate those words into what symbol are you really looking for up here. So all those symbols have to have a meaning in your head. What are you really looking for? I think you're looking for this y coordinate, right? Where is it up and down? They don't care. This question has nothing to do with what it did sideways. Where is it up and down? And then how are you going to tell the equation that it's there at that peak? I think you've got two ways to tell it's at the peak.
From the seconds?
What's that?
From the seconds?
From how long it's been traveling. So you could say, well, what is the y change in position when t equals 6 seconds? But that would mean that you already analyzed that 60 meters per second. You can see that that's going to run into a 0 in 6 seconds. If you didn't do that, there's another way. How do you know when you hit the peak?
Final y velocity equals 0?
The final velocity in the y direction is 0. In other words, when you look at your kinematics, if you force that to be 0, but it also shows up here that to be 0, and you know the starting speed, then you can either find something with time, or you can find out something with position. Yeah, here you're asking something about position, so I like the looks of this last one right here. This last one should do that. So when I read that question right there, I'm kind of thinking I'm going to use something like this. Exactly the same equation that you saw before. Oh, let me see, we're looking for position, so we want a square cubed. Square, so plus 2 acceleration in the y direction. Okay, so any vector that goes that way I'll call positive, any vector that comes this way is negative. So I have to read those words and just kind of figure out exactly what it's really trying to tell me what it wants to find. That is this change in y position, and at the peak I can force this number right here to be 0. So at the peak, it's not going up, it's not coming down, that's that. But initial velocity in the y direction, what do I put in for that? This number, an arrow at an angle, never goes into an equation. The equation is looking just for what's going on sideways or up and down. That number right there is that number right there. It's not this one right here. That's too complicated. If I could do anything with that, then I would have done this. Why do it if I can just deal with the 100? But I can't deal with the 100 because it's at a stupid angle. So I can't deal with stupid angles, so I have to do just straight sideways and straight up and downs. That's all I can do. But this thing right here, that guy right there, that's this right there. What is it doing up and down? Period. And it's going up at 60 meters per second. That's going to get squared. Gravity affects things up and down. So that's going to get a minus sign. And that should be one equation, one unknown. That should tell me what it's doing up and down. So 60 squared, I think that's just 6 times 6, 36, with a couple zeros added on, and I bring it to the other side, it becomes negative. And then I'm going to divide both sides by negative 20 meters per second. So it looks like 2 into 36 is what, 18? This is maybe 180 meters or something. So I think when I try this on a calculator, The seconds are gonna cancel out. So it looks like that y coordinate is 180 meters at t equals 6 seconds. So 6 seconds, yeah, it's y coordinate 180 meters high, which is exactly the answer to that question. How high did it go? Okay, it looks like there's a last part here. Where will the ball hit? So I think those words really mean, where does it hit on the ground here, right? In other words, how far sideways did it really go? So it doesn't say that, but I have to, interpret those words. It's really asking, what's his change of position sideways, just as it smacks into the ground and so forth. So this is actually part B here. So let's call that part B. And then part C. That's all I need for anything that's happening sideways, because there's no acceleration. So it's just distance equals rate times time. How fast is it going sideways? 80 meters per second. It's that number. That's how fast it's going all the time, until it hits the ground. So it's going 80 meters per second, and we'll just say it's going that way, and I'll just call that way positive. And it's going that way for how long?
12 seconds.
12 seconds, 6 seconds to the peak. Because it takes 6 seconds to get that to 0, so it's in the air for 12 seconds. So 8 times 12 is 96, and I have to add a 0. This is a good projectile. This seems like 1 mile. $960. Okay. Same type of questions you handled in chapter 2, except that there's really 2 problems. What's it doing sideways? What's it doing up and down? This, because there's no acceleration, is simple enough to handle. This right here is not hard, but you do have vectors up and down and so forth. So you always are going to have gravity down if projectiles are usually going to be thrown up. Or somebody can throw them sideways and so forth. But any question on this one here? What I've really got going on here in this paper is a chapter 2 issue, and then I've got a chapter 3 issue too. So we can compare the motion of what's going on in chapter 2, where things are just moving in a line, in chapter 3, where they are moving in more than one dimension. So let's take a look. It says that that there is a little scale here, okay, from 0 to 16 centimeters and so forth. And we're going to use some kind of scale. That 1 centimeter on the paper stands for 5 meters in real life. Okay, so we can actually do this really the kind of scale and so forth here. And so take a look here in, this is the chapter 2 problem, where you're just dropping something and it moves just in a straight line. Okay, so where is that object? Where is that object? You just drop it. Where is it after falling for 1 second? How far did it fall? There's a sucker answer to this, and that sucker answer will be part A in the test. And the sucker answer is 10 meters. Did it fall 10 meters in 1 second? It did not. Why would you think that? I have no idea why you think that. It's a calculation. Where is hard to do because there's squares there. Where is it after 1 second? Where? Change of position. If I just drop it, what does that mean for this equation if I just drop it? Initial velocity in the y direction is 0. That ball dies. Let's just call gravity 10. 1 second, 1 squared is 1 times 10. 10 cut in half. 5 meters. On Earth, when you drop an object, it has changed its position by 5 meters. Now, using that scale, where is it?
1 centimeter.
1 centimeter down. So 1 centimeter down. So it's like right there. Okay, that's chapter 2. 2 seconds, I'm gonna let it fall for 2 seconds. Where is it? Well, it still started from 0. 2 squared, 4 times 10, cut in half, 20. Using that scale, 4 centimeters down the page. So 4 centimeters. Okay. Let it fall for 3 seconds. Where is it? Well, this tells me the change in position for any time that I want to plug in here. So I'm going to put in 3. It's still, I just dropped it. It still started from 0. So I'm going to let it fall for 3 seconds. 3 squared, 9 times 10, 90, cut in half. 45. But then I have to scale it to fit on the paper. So 9, I mean, right? So if 1 centimeter equals 5 meters in real life, this is at now 9. Okay, so, without doing any calculations, do you know where the next one is? 1, 4, 9. What? 16. They're not square roots, they are perfect squares. Yeah. 1 squared, 2 squared, 3 squared, next one's gonna be 4 squared. When Galileo is looking at data, he knows he's dealing with a parabola, right? You're seeing that this is going up by the square and so forth. Next one is down here. In other words, it's just smacking into the ground at 4 seconds, right? So at 4 seconds, it's going to be hitting the ground. So if I put in 4 here, 4 squared is 16, times 10 is 160, cut in half is 80, then I scale it, it's down at 16. But yeah, I see 1, 4, 9, 16. If the ground wasn't in the way on the ruler, where would it be the next second? 25, all right? 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Something is increasing by the square. So when we say that Galileo, guesses this at the data, you don't have to be a giant genius to know that you're really dealing with parabolas and so forth. And we need to use that 1/2 to make sure we get the right data and so forth. Okay, that's chapter 2. Now, chapter 3. Now somebody is throwing it, and look how they threw it. They threw it completely sideways. And I really like the way it's drawn. Completely sideways. Notice, a certain distance, and then there's the ball. A certain distance, the same distance, and then the ball. A certain distance, and then the ball. A certain distance, and then the ball. That is, if there were not a planet and you threw it sideways, that's what it would do. It would just keep going sideways at constant speed because there's nothing to speed it up or slow it down. Sideways